water, it's great to be fishing. But fog does tend to dim your enthusiasm. Don't despair. Your handy compass works in rain, hail, and yes, even fog. Unless, of course, there is something which throws the compass off. In which case, you might be in for a bit of a surprise. A compass needle is simply a magnet, and an attractive force exists between magnets and iron objects, even at a distance and even through the vacuum of space. It's as if invisible hands pull the magnet and metal together. In this way, magnetism is similar to the forces that charged particles exert on each other. These forces act over a distance in the same mysterious way. During the 17th and 18th centuries, electricity and magnetism developed as separate sciences and were believed to be unrelated. Then, in 1800, Alessandro Volta developed a device that paved the way for a change in this view. His device consisted of copper and silver coins, arranged in a column and separated by pieces of cardboard soaked in salt water. When he attached a conductor to the top and bottom, like this, and brought the two ends together, a spark resulted, indicating that a flow of charge was occurring. Volta's work eventually led to the development of batteries, which could be used as sources of continuous charge flow. A battery like this was used by Danish physicist Hans Christian Ørsted in 1819 to conduct an experiment in which he hoped to prove conclusively that electricity and magnetism were not related. At first, the demonstration seemed to work. When the switch was closed, the compass needle, which was perpendicular to the conductor, didn't move at all. However, when Professor Ørsted repeated the experiment, this time with the needle parallel to the conductor, and the switch was closed, the compass needle reacted instantly. So it seemed obvious that electricity and magnetism were somehow related. As a result of Ørsted's experiments, French physicist André Ampère made a detailed study of the magnetic field about a conductor carrying a charge flow. Using iron filings, he demonstrated that there was a magnetic field around the conductor. The pattern formed by the iron filings created a series of concentric circles. Depending on which way the negatively charged electrons flow through the conductor, the magnetic field around the conductor will be in one of two directions. With the electrons flowing this way, the magnetic field around the conductor is in this direction. Reversing the flow of electrons doesn't affect the shape of the pattern, but it does affect the direction of the field. Reverse the electron flow through the conductor, and the magnetic field direction will reverse as well. Our left hand gives us a convenient method for correctly predicting the relationship between the direction of the magnetic field around the conductor and the direction of electron flow through the conductor. This is the left-hand rule for conductors, and it states that if the left hand is placed around the conductor, with the thumb pointing in the direction of electron flow, the fingers will curl in the same direction as the magnetic field. Reversing the current means that the thumb must now point in the opposite direction. Although the fingers now curl the other way, they nevertheless indicate the new direction of the magnetic field. Of course, if the flow of charge is interrupted, the magnetic field collapses immediately.